Welcome everyone. My name is David Rapson. I'm the Operations Manager of FCT ACTEC. I've been with FCT for more than 20 years in various technical roles, mostly based in the cement industry. Today I'd like to share some exciting results with you from a cement plant that's benefited from an at-line raw mix control system. Some recent advances in technology have made online process control much more effective and affordable than it used to be. There are lots of variations throughout a cement process, but we can do a lot to reduce those now by choosing raw materials that have consistent properties and also fuels that have consistent properties. There are many techniques that can be used to reduce the variations of these, including mixing, blending, and homogenizing. Every plant will use these techniques to reduce the variations at each stage in the cement process. Sampling and testing are key in the process in order to reduce variability and to eliminate out of specification material. More frequent testing offers a greater insight into the process, and with well-chosen controls will reduce operating costs and improve the quality of the product. Reducing variability of all the inputs to the kiln will improve the stability. This includes the raw materials, the fuels, the alternative fuels, and any recirculation that might come back, like kiln dust or other materials that are often put into cement kilns. On most plants, testing is still done manually every 2 to 3 or even 4 hours. And the time lags associated with that mean that there can be a lot of changes that go on and the testing becomes out of sync with the process. At-line and online control has been wanted for decades, and the cross-belt analyzers were some of the first that came into the systems. Sampling is more frequent and often automated. The software has developed a lot in recent years and is now able to do far more complex calculations more quickly. Recent advances in computing power, X-ray detectors, and low-powered tubes have all meant that a new range of process equipment is much more affordable. Configuring an at-line system is relatively straightforward. It's a matter of choosing what sort of results that you need, and then once that's happened, the sampling location and the sampler can be selected. Often the supplier can help with both of those. Once the analyzer is chosen, the sample preparation can be worked out and also the means for returning the sample. Control software is required, and that can come from either the plant provider or there are a number of third-party software vendors available now also. Most plants already monitor critical parameters, but the opportunity exists to measure more now. For example, fineness or particle size analysis can be measured at the same time as elemental chemistry and also mineralogical chemistry. Often the best sampling location is already being used, but automating that in older plants can be a bit problematic. It's best to seek advice from reputable suppliers about getting the sample and transporting it to the analyzer. Where possible, use gravity to simplify the sample transport arrangement. In this photograph, sampling at the discharge of the air slide is the preferred location. But there's going to be compromises here because there's lots of other equipment located nearby. The choice of sampler will depend upon the material being measured and the requirements of the analyzer. While not always being ideal, some of the existing samplers can be reused because the plant knows what to expect and has history of results coming from that sampler. They understand any bias that might be presented with those samples. There are different analyzers available for each type of requirement. These techniques will be determined by the results that are required. Particle sizing is done with lasers. Elemental measurements are done with XRF methods. and minerals are measured with XRD techniques. There are now new generations of online analyzers available that are very accurate and can give results every 2 to 3 minutes. They can use XRF techniques to measure elements or XRD techniques to measure minerals. One major advantage of these new machines is that they do not use radioisotopes, which are very costly and require often lots of paperwork. These units are rugged and designed to operate in the field close to the sampling point, usually underneath it. In many applications, little or no sample preparation is required because it's all done inside the machine. The analysis results are not affected by layering either. All the preparation is included inside the machine. The results are sent to the PLC and they can then be sent on to proportioning software to control the feeders or whatever. So these units are designed for process control and can provide many times the amount of process data to give new insights into the operation of the plant. This is the surge hopper on an RMX raw meal analyzer. The proximity sensor is used to control the sampler or the diverter that's going to bring material into the machine. Inside the analyzer, a fixed amount of material is transferred to the sample preparation area. So the material is presented to the X-ray beam at a constant rate of about 150 grams per minute. This ensures very good particle statistics. I'd now like to present some results from a cement plant in the USA, which recently installed an RMX analyzer. This plant is producing 1.7 million tonnes per year of clinker and wants more consistent feed chemistry to improve kiln operation. The plant has a chevron stacker reclaimer system for the raw materials, which creates kiln instabilities at the end of each heap. They have a cross-belt analyzer for the limestone and another one for the mix control. The problem is that the cross-belts can't measure coarse feed material that's coming back from the raw mill, and they can't measure kiln dust, which is being added to the raw meal as well. So by measuring raw meal directly, all the streams can be accounted for. So this is the configuration for the RMX raw meal analyzer. You can see the sampler is located after the raw mill, and in this location it will include carryover dust and any recycled material that's come from the mill. Plant currently samples raw meal after the mill, and the same sampler is going to be used again for the at-line analyzer system. Material falls from the sampler into the analyzer shack below. This is the XRF raw meal analyzer mounted on its automatic sample return system in a small hut. The raw meal drops from the sampler above into the analyzer hopper, where it is mixed and prepared continuously for the sample presentation. About half a cupful of material passes through this machine every minute. After analysis, the meal is pneumatically returned to the process. At the front of the machine is a sample composite bucket, which is provided to the laboratory every 4 hours. That material is used to compensate for any drift that may have occurred. The plant PLC controls all of the equipment in the analyzer system. When the analyzer hopper is low, that requests more sample and ensures a continuous flow of material through the machine. The analysis results are also sent to the PLC for processing and subsequent control actions. This is a screenshot in the control room showing all the feed silos and their weigh feeders. The feeders use variable speed drives which control the rate of material being discharged from each bin, enabling very accurate proportioning. Pre-blend material from the reclaimed stockpiles also receives rejects from the raw mill table, complicating this installation. So this graph shows the elemental chemistry of the raw meal every 3 hours based on the laboratory results, and it covers a 2-day period. The silica value, which is indicated as high, is the giveaway that there's been a pre-blend heap change, and really this is the only way of noticing that change. So in this graph, we've added in the 2-minute data from the outline analyzer and superimposed it on top of the lab results. And you can see there's a lot more happening than was visible with just the 3-hour data. Here I've added a vertical line when the heat, after the heat change, but this is when we've turned on the RMX analyzer, and it shows how it's responded to the variations in chemistry. Despite not being fully tuned, calcium and silica trends have stabilised very quickly once the software took control. As part of the commissioning, these loops have been better tuned to reduce the variability in the ringing that's obvious here. So these graphs show the clinker results and for the C3S before and after the raw mix control system was turned on. The plant has been able to make use of the reduced variability from the improved kiln stability as a result of having the continuous data available. The plant has decided to increase their C3S target from 60 to 64, which they were never previously able to do. So this is the same clinker data as the previous slide, just presented a little bit differently. So there's a box and whisker plot here. What this is showing is that 50% of the values are inside the box. Another 50% of the values are outside of the box, shown by the 2 lines. X is the mean and the line through the box is the median. So here the blue box is smaller than the orange one, confirming that there's reduced variability. The plant is, because of that reduced variability, the plant is now able to operate at 64% C3S with a much reduced standard deviation of 3.6, something that was just not possible previously. So here's the raw freelime data from the kiln. There's a broad spread in the data and it shows some very high freelimes indicating still kiln instability. Once the at-line system was in control, it's obvious that the kiln is more stable and there is less high freelime values. So again, I've paired the freelime data here in the box and whisker plot. And the at-line data in the blue shows less outlier points above the graph, which means there's been less off-spec material going into the fringe silo. The average freelime is slightly lower, now at 1.2%, but the kiln's operating at a higher C3S target. So the plant's been able to improve its kiln stability with increased C3S to give them better early strengths, only reducing the freelime a small amount. The plant staff have made a number of comments about the operation of the plant since the introduction of the automatic online raw mix control system. The kiln operators report that the mix is easier to burn and the kiln is easier to control. Before we had to target a lower C3S to assist with kiln operation. Now we can target 63 to 64 and achieve higher early strengths. Now the analyzer reports as soon as the composition goes off, and the process software starts the correction process right away. So in summary, this case study has shown that using at-line analysis of raw meal for mix control will stabilize the kiln and the clinker will be easier to burn. The more stable kiln, the plant chose to increase its C3S target to increase early strengths, something that they were never able to do before. The increased sampling frequency of the raw meal revealed variations that could not be seen with standard laboratory testing. The additional at-line data included the kiln dust and the raw mill recycle material, which gave more accurate control of the feeders, further reducing variation. The at-line analyzer has shown that it's an essential tool for stable kiln operation and has enhanced the clinker quality as well. Thank you.